Now, I am a firm believer in all of the pros that come with IPv6, and a lot of enterprises are now moving towards the IPv6 world. But here's the thing, when it comes to IPv6, it can be a little intimidating at first, and what we now have to talk about is how to actually implement IPv6 in an enterprise environment. What we're really talking about now is transitions from IPv4 towards IPv6 environments. This is kind of a unique situation where we could either have both IPv4 and IPv6 coexisting side by side, or we could have some IPv6 only environments that need to traverse IPv4 networks in order to talk to each other. By the end of this skill, we'll have covered the three main methods for actually transitioning to IPv6 environments. That's the dual stack method, the tunneling method, or the translation method. So get ready as we have some fun talking about how we can implement IPv6 in an enterprise environment. Let's get going. Our first IPv6 transition method is going to be overwhelmingly the preferred way to implement IPv6 in your environment. It's going to be the dual stack environment. This is where we're running IPv4 and IPv6 on the same box, on the same interfaces. They're running at the same time. Now, it's an interesting concept because this is what most enterprises are going to be using. This is what they're going to be preferred to be using before they transition to IPv6 only. This is going to be the best way to make sure that all of our IPv6 services are up and running too. So let's talk about how the dual stack environment really works and how we can implement it within our own environment. So here's the real thing when it comes to IPv6. Most modern operating systems that we work with today, like Windows 10, Mac OS, or even our iOS devices or Android devices, prefer to use IPv6 first. If they have an IPv6 address, it's going to attempt to actually get an IPv6 established session going first using DNS or any other TCP. It's going to try and use IPv6 before it attempts to use IPv4. So that's a good reason why we would want to implement IPv6 in our own enterprise in the first place, is just that that's the preferred method of connectivity for all of our operating systems that we work with today. Beyond that, there's a lot of other benefits that come with IPv6 that we talked a little bit about when we talked about IPv6 schema designs. Now let's talk about the first IPv6 transition methodology, and that's going to be using the dual stack IPv6 transition methodology. When we say dual stack, what we're really talking about is using both IPv4 and IPv6. You can use them on almost every device that's in production today. That's kind of the thing is, we have all of these transition methodologies. We're going to talk about tunneling and translation later. And one of the reasons that we wouldn't use dual stack is because the devices that we're using in our enterprise simply don't support IPv6. But look, here's the thing, we're in an era now where pretty much everything supports IPv6. So that's why pretty much everyone who's going to be deploying some form of transition technology is just going to run dual stack. There's not much of a reason not to at this point because it's just easier. So all we have to do, you've already seen this in action when we talked about IPv4 schemes. I'm going to be picking on switch 16 here, this Ethernet 1.2 link, and router 23 here, and this Ethernet 0.1 link. All we have to do is just turn IPv6 on and then tell it to configure its own IP address, where we assign an IP address. We talk about all of that again with auto config and stateless configuration in DHCPv6. So check this out. If I look at switch 16 here, the first thing I have to do is I have to turn IPv6 unicast routing on. You have to turn it on by default. Some of these devices don't come with IPv6 turned on by default. If I exit out of configuration mode, now I can give it a show IP interface brief just to prove that we are running IPv4 IP addresses. And if I recall, the address, the interface that we're looking at here on the switch is Ethernet 1.2. So if I look back here, Ethernet 1.2 right there has this IPv4 address. If I do show IPv6 interface brief, nope, not 5, 6, I see Ethernet 1.2 has no IPv6 address assigned to it. So I can go into configuration mode, interface Ethernet 1.2, and I can simply say IPv6 address auto config. If my router was running some form of route prefix delegation or doing router advertisements, we could do it that way. I can also explicitly assign an IPv6 address from a subnet that I have globally routable. I can say db8 dead beef, and I can tell it just use EUI64 to come up with that address. So now if I give it a show IP interface brief, I see that I still maintain my IPv4 address. If I give it a show IPv6 interface brief, now I have an IPv6 address on that interface. Notice again that it is using that EUI64 formatting. Right here we see on both of these addresses, it squeezes in the FFFE right in the middle of that MAC address. And that's really all there is to it. All we have to do is turn IPv6 on the interfaces and allow it to use both IPv4 and IPv6. When it comes to actually transitioning, because that is the name of the game in this skill, the idea is that you're trying to get away from IPv4 onto exclusively IPv6. So the idea is that you would design subnets throughout this entire enterprise here, all the way down to all of your hosts, meeting those host requirements. Not very hard to do in IPv6 because there's just so many addresses. But then eventually, once you verify that end-to-end IPv6 connectivity is in place, and you have things like DNS and DHCP, or stateless configuration, once you've verified that all of your services are working correctly with IPv6, you can simply start to peel off IPv4 if that's what you want to do. Now, most of the world still operates on IPv4, even though you can run IPv6 on top of it, and our operating systems prefer to use IPv6. But that's all there is to the dual stack method, and that's why pretty much everybody is using it these days, because now our devices all support it. IPv6 is the preferred usage for operating systems today, and all you have to do is turn it on. So that's been understanding the dual stack transition methodology. I hope this has been informative for you, and I'd like to thank you for viewing. Remember that the name of the game in this particular skill is IPv6 transitions. This is where we're going from IPv4 to IPv6. And in a lot of cases here, there are segments or portions of our network that are hard to get off of IPv4. We could deploy a new site with IPv6 only, already running. It's a greenfield deployment, but at some point it's going to hit an IPv4 wall, and this is where we have to implement something to help that IPv6 traffic get out into the IPv4 world. Our first transition method that we're going to talk about now, since we don't have dual stack as an option, is going to be tunneling. This is where we can use dynamic tunnels or manually created tunnels to help us get that IPv6 traffic from point A to point B with IPv4 in the middle. Let's get talking about IPv6 tunneling transition methods. Now we're moving on to some more interesting use cases for when we need to deploy IPv6 between sites where we can't deploy IPv6 in the middle. What we're really talking about here is pretend for a moment that this is one of our sites right here, and this is another one of our sites right here, but maybe it's separated by the internet, and all the ISP will support for us is IPv4. This is a situation where we have IPv6 traffic that needs to get from site 1 over to site 2. Now we've got these labeled right here. On R1, the Ethernet 01 interface only has this IPv6 address. Notice it starts with a 2005, blah, 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 blah. And the E01 interface on R3 only has this IPv6 address. It starts with a 2007. What we really need to have happen now is we need to build a tunnel over the internet that will tunnel IPv6 traffic inside of an IPv4 header. So that way the internet router here sees a source and a destination of an IPv4 address that it knows how to route to from one site to the next. But inside of that packet is actually containing our IPv6 addresses. There are a few different ways that we can actually make this happen. The first one, and maybe one of the most preferred ways to do this, is to manually create a tunnel. This could be using something like GRE. In this case, when we create a manually created tunnel, let me kind of just erase some of the screen here so that we can actually see what this is going to look like. When we manually create an IPv4 GRE tunnel, it's kind of like just removing this from the picture altogether, and these devices just see a direct connection like this. It's a lot like an IPsec tunnel. And then our tunnels will have IPv6 addresses like an IPv6 subnet. So the tunnel subnet will represent this link right here, this logical link that exists over the internet. and then they can exchange routing information between each other. So in this exact topology, this is how I've actually created this. I've manually created a GRE tunnel that says the IPv4 source and destination are these outside addresses that are used by the internet. But logically, they use these IPv6 addresses to route between each other. Then we can start running protocols on IPv6 to share routing information. So here I've turned on ISIS between this subnet right here so that a neighbor adjacency forms, and then I turn on ISIS on these interfaces, and guess what? The neighbor adjacency comes to life, and they now know how to share information to each other. So when a host on the 2005 network needs to ping a host on the 2007 network, it knows that its next hop is 2001, whose then next hop is to use the tunnel interface. Let's check it out. Over here on R1, I'll give it a show IP interface brief. You can see this is our outside IP address to 10.0.0.1. It's very simple. And notice that the tunnel interface that I have created here does not have an IPv4 address at all on it. If I give it a show IPv6 interface brief, we can see here's the 2005 network that's going to be on my host side of things, and then the tunnel interface as the 2001 network. Now check this out. If I give it a show IPv6 route, you can see this is where I'm actually running ISIS. And we can see that over the tunnel, we've actually learned about the 2007/64 network. Notice that the next hop is going to be a link local address. This is going to be for that device over on the other side of the tunnel, but it is using the tunnel interface as its exit point because that's how it's logically configured. Now, if you're interested at all in the configuration of how to make this happen, don't worry about this for the ENSLD exam. This is actually more of an NARCI topic, but you can see it right here. I can do a show run interface tunnel 0. And this is what the interface configuration looks like. We set an IPv6 address, we set our source interface, our destination IP address is the IPv4 address, and then I simply turn IPv6 router ISIS on. Just for fun, I can also show you the show run section ISIS, and you can see it looks kind of like this. I set a net address. I also have to turn it on for the address family IPv6. Just for fun, I redistributed connected and static routes, and that brought it all up to life. Now, as I said, this is primarily for manually creating interface tunnels, but there are dynamic and automatic ways of creating interface tunnels too. One of the most popular ones is called the 624 tunnel, and this is a lot of times deployed specifically on routers. Now, I'm zooming in a little bit more on the screen so that we can talk more about the 624 tunnel. This is going to be one of the more popular forms of IPv4 tunneling, and it sets up the exact same scenario that we had before, where we had our two sites. They're kind of drawn like this, where we have an IPv6 site running here with R1 and an IPv6 site here with R3, and it's separated by an IPv4 internet. Now, it's important to know that these outside interfaces right here, the E00 on R1 and the E00 on R3, have globally unique IPv4 unicast addresses. These are not private IPv4 unicast addresses because the RFC that created 624, RFC 3056, dictates that we must have globally unique IPv4 addresses. Why? Because we're actually going to use these. See, check this out. We'll actually show you the RFC right now, and here's what's going to happen. I'm going to read you the entire RFC. No, I'm kidding. I would never do that to you. But the RFC actually dictates something that's pretty unique and interesting right here. And this is how the encapsulation is going to work. We're going to be taking our IPv6 packet, and we're going to be putting it inside of an IPv4 packet. And rather than manually creating our own addressing and our own tunnel mechanisms to make this happen, this RFC and the 624 configuration automatically creates the addressing for the tunnel. And we know that this has been automatically created because this is exactly what the RFC dictates. First of all, a 624 prefix will always begin with a 2002:/16. So our devices, when they see a 2002 IPv6 address, they'll know, wait a minute, this IPv6 content that I'm de-encapsulating has been tunneled via 624. But that's not where the buck stops. The next 32 bits that comes after this is actually taking that globally unique IPv4 unicast, encoding it into hex, and then putting it immediately after the 2002. So using this clever tool right here, this IP address to hex converter, I can type in a globally unique address like 191.168.2.1 or something like that, and convert it to hex. The result that comes back is this BFA80201. We would then expect the first 48 bits to be BFA8:0201 because that was the 191.168.2.1. Do you see the 2 and the 1 right there? And this is exactly what it's illustrating right here. The prefix length is going to be the first 48 bits. It's going to consist of a 2002 to comprise the first 16 bits, and then the next 32 bits right here is going to be the V4 ADDR or the V4 address. The last 16 bits are going to be an SLA ID, which means the total prefix here is going to be 64 bits in length. And then the interface ID, or basically the host address, is what makes up the last 64 bits of the entire IPv6 address. So if I jump back to the diagram here, all of a sudden we see that this IPv4 address matters because that is what's actually going to create our tunnel address. 2002 : whatever this IPv4 address is in hex, then the SLA ID /64. That's going to be our 624 tunnel. And again, this gets auto-created when we go to configure the actual interface itself. Check it out. This works in a similar configuration method where we create a tunnel interface and all we have to do is set the tunnel mode using IPv6 IP, and then you specify what kind of automatic translation you want to do. Check this out. From R1, I'll actually kind of set up the other automatic items that we're going to talk about. I'll go into interface tunnel 0, and I'll do tunnel mode and press question mark here, and you can see this is the IPv6 over IP encapsulation that will automatically perform these types of translations for us. So if I say IPv6 IP, then hit question mark, look at the options that we have. Here's 6 to 4, here's 6RD, and here's ISATAP. We're going to talk about all of those in just a second. We've already talked a little bit about 6 to 4, and this is how our tunnel interface would know to automatically perform this type of encapsulation for us, rather than using a GRE header and performing some form of encapsulation that adds some extra payload or heading to us. This is an automatic form of encapsulation that we should know about. Now, the next one we're going to talk about is 6RD, or 6 rapid deployment. In this case, this is more of a service provider technology. We've got the same situation where we have these borders handed to us, but instead of being restricted to the 2002 prefix where we manually configure the tunnel mode ourselves, what we're going to have happen here is the service provider will delegate a prefix to us for use in IPv4 encapsulation. So in this case, when we say the 6RD, or 6 rapid deployment, one more time, our tunnel interface will be using whatever IPv6 subnet that the service provider has told us to use. In fact, in a lot of cases, we don't perform any encapsulation. The service provider actually has an edge router somewhere like right here that performs this encapsulation for us. The point is that you should know we're not restricted to manually creating our own GRE tunnels or restricted to the 2002 prefix. The service provider will provide us with the prefix, and either they will perform the encapsulation or we will perform the encapsulation, and then they will carry it over their IPv4 backbone. That's what 6RD is all about. Now, the last one that we saw was ISATAP. This technology, again, is solving the exact same problem that we've seen here, where we've got an edge of IPv6 addresses separated between an IPv4 network. Where you see this more commonly is actually on host devices themselves. When a host device creates its own IPv6 address, and then it may connect using a VPN tunnel that's only IPv4, then you may see it create an ISATAP address. The ISATAP address is a unique one because it doesn't necessarily have to use a global unicast address. It could use a link local address, an FE80. But this is where it's a little bit different. The ISATAP address is going to look kind of like this. You're going to have your 64 bits of addressing. Let's just kind of write it out. I'm going to write it out fully instead of using the double colons. So this is my first 64 bits that sets up my ISATAP address. The next 32 bits are going to be 0000 colon, making sure my head's not covering the screen here, 5EFE, and then what happens is we take our 32-bit IPv4 address and translate it to hex and put it right here. Now again, this is auto configuration. It will figure this out on its own. But what we would be doing is we would be taking something like 192.168.1.1, translating that to hex, and then putting those 32 bits tacked onto the end of it. And that's how these devices would create their isotap tunnels. They would then recognize because of these 32 bits right here, the 0005EFE, they would go, oh, in that specific spot, those 32 bits indicate to me that this is an isotap address, so the remaining 32 bits are actually the IPv4 address, and that's how a lot of hosts are actually using isotap to tunnel their IPv6 traffic over IPv4 networks. Again, primarily you see this when you see it using like remote access VPN technologies. So that's been understanding how the tunneling technologies could help us connect IPv6 sites over IPv4 networks. I hope this has been informative for you, and I'd like to thank you for viewing. Now that last nugget with IPv6 tunneling was pretty fun and it's pretty cool. There's a bunch of different technologies that we can use right now on our Cisco command line to get our IPv6 sites up and running in IPv4. But remember, when we're talking about design, there are some major components, or really three big tenets, that we should consider when we talk about design and network deployments in general. Those three tenets, again, are things like stability, scalability, and security. Now, this nugget is going to be all about the security of IPv6 tunneling over IPv4, and one of the things that you might not have thought about real quick. Let's get going, checking out how we could secure our IPv6 over IPv4 environments. This actually blew me away the first time I saw it, because what we're really talking about at the end of the day is the OSI model itself. That's right, we're actually talking about how does traffic in between IPv6 sites get inspected. You got to think about this, because we may want to put things like intrusion devices or firewalls or security appliances in between our IPv6 sites, but does it actually carry the traffic that we want? I mean, think about this. Think about the OSI model itself. We've got layer 1, which is the physical layer, of course. We've got layer 2, which is the data link layer. Then, this is where it gets interesting. We've got layer 3. Now, this is going to be the network layer, and this is typically where we talk about the IP protocol itself. So let's pretend host 4 wants to ping host 5. If these were only separated by one router and they were all speaking IPv6, it would have a source address of 2005 and a destination address of 2007, blah, 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 whatever, /64. But in this particular topology, that's not the case. We have this IPv6 site and this IPv6 site. We're speaking IPv6 here and IPv6 here, but in the middle, our transport between them is speaking IPv4. And we talked about things like tunneling. We're going to talk about things like translation. But if we use something like tunneling, like 624 or isotap, or even manually creating something like a GRE tunnel, what happens here? Our IPv6 traffic is going to be contained inside of an IPv4 packet. So at layer 3, as this traffic traverses the firewall right here, and the return traffic traverses the firewall right here, it's going to be speaking IPv4. Now let's pick on the GRE tunnel for just a moment, because the others are kind of the same thing. It's all just the gist. We're just going to use the GRE tunnel as an example. The GRE tunnel is going to be speaking on the IP protocol number 47. And that sets up that everything above it is then going to be an IPv6 packet. There's going to be a source and a destination, and then the payload itself above this. But to the firewall, it has to be smart enough to actually look at this and go, wait a minute, I've got a packet inside of a packet. And if I want to inspect this packet correctly, I need to make sure that I go layers deeper and actually look at the IPv6 traffic that is traversing my network. I don't know why, but this really blew my mind the first time I saw it. I'm like, wait a minute, I didn't even consider that, because My firewalls may only be speaking IPv4, and they may not know about GRE inspection, and they may not know that they need to inspect traffic. Because what could really happen is a bad actor, like a hacker, could come along and send its IPv6 traffic in, and it could reach the other sites maliciously. Or it may go out to the internet, being tunneled to its own IPv6 site, and our firewall would be none the wiser because it would only be looking at IPv4 transit information and going, well, I don't know anything about GRE or 624 or ISATAP, you're good to go. And it would allow malicious traffic to actually transmit over our firewall and out to the internet or transit from one site to another. We could be doing things like exfiltration techniques or eavesdropping techniques or injecting spoofing type of information, or even performing DDoS attacks like botnet information. So let me show you a real-world demonstration of this in action. I'm going to start a Wireshark capture right here on the E01 interface. Then I'm going to ping from R1 to R3's E01 interface, this 2007 interface. We'll then be able to inspect the traffic, and one of the cool things about Wireshark is it is smart enough to look a layer deeper once it sees GRE packets. This is setting up what we would want to expect from our firewalls themselves. So I'll start the packet capture on the firewall's E01 interface. We'll watch the traffic flow back and forth. I'll click OK. There, the packet capture is now running. I'll kind of move it out of the way so I can bring up R1. And now I'll move it out of the way so I can bring up R3. And from R3, I'll say show IPv6 interface brief. That way I could actually get the IP address that I'm trying to ping. It's this 2007 address. This is that FAR address on R3. So I'll highlight it, and over on R1, I'll say ping IPv6, and then paste in the remote address, and this will generate some IPv6 traffic that goes over the tunnel. We've got round-trip traffic. Very cool thing to see. Back over here, I'm going to stop the Wireshark capture and expand it. Right there, we can see where, in this pink section, we can see where our Wireshark capture was smart enough to look inside the packet and expect it to see that it was actually running ICMP v6 is the protocol that was being transmitted, not IPv4 with GRE. Let's look at the very first packet here. Immediately, we see layer 1, layer 2, and layer 3. We see the source address is my IPv4 information. This, again, is what we would expect our IPv4 speaking firewall to see, but we would need it to go, wait, what are you carrying on top of you, IPv4? And it would see, oh, I've got GRE with IPv6 traffic that I'm carrying on top of me. That means I need to go deeper, and this is where it starts to see the real source and real destination and the real protocol that is being transmitted there, which is ICMP v6. Very cool that Wireshark can capture the back and forth, and that's kind of indicated by this little line over here. The session and response traffic is what that little information, that little symbol is that we can see. So then we see the reply that's coming back, and then we see the next packet, and then the reply that's coming back. And notice how the IPv4 source and destination is also changing. Major talking point that you should consider is why would we need this? Where would we need this? How would we need this? Well, GRE is oftentimes deployed with IPsec. In a lot of ways, this is to use for DMVPN as well as SVTIs. That's virtual tunnel interfaces. And GRE, by default, doesn't provide the encryption that lots of times that we need. So these are often deployed together. The cool thing about this, though, is that IPsec doesn't have the ability to transmit some of the other traffic that we need, like multicast traffic. So it makes a lot of sense to deploy GRE and IPsec tunnels together because GRE can carry the payloads that IPsec can't, but IPsec can provide the encryption that GRE can't. They are working together. But when we deploy this and we want to tunnel IPv6 traffic over GRE, we need to make sure that our firewall that sits in between or in line, if it's routing or not, it needs to be able to inspect those higher layer protocols. So in this case, it can make sure that nothing malicious is actually happening by hiding IPv6 traffic inside of IPv4. So this is a big consideration you should think about when it comes to deploying IPv6 transition techniques, is that at the end of the day, the transit networks are still only speaking IPv4, and our traffic that we could actually be carrying is IPv6. The firewalls, intrusion devices, or security appliances need to be able to inspect above IPv4 to actually look at the real payloads themselves and make sure this traffic is still valid to actually be transmitted from one site to the next or out to the internet. So that's securing your IPv6 tunnels. I hope this has been informative for you, and I'd like to thank you for viewing. Another IPv6 over or through IPv4 technology that we could consider is Lisp. That's Location Identity Separation Protocol. Now, Lisp has been primarily used in service provider networks to help scale the internet itself, but we're seeing it pop up more and more and more in enterprises these days because of SD access. So you're going to learn a little bit more about SD access and how Lisp plays into that later in this playlist from Jeff Kish. But for now, what we need to do is introduce the Lisp protocols. What are the components that make up Lisp, and how then does that translate to IPv6 over or through IPv4 translation? This is going to be a big nugget, but it's going to be a lot of fun, and it's really going to set you up for success when you start learning more about SD access in this playlist. So get ready and buckle up as we explore how Lisp can be used to tunnel IPv6 traffic over IPv4. Let's go. Now, through my studies of learning SD access as well as the Lisp protocol, I have rarely encountered a couple resources that could explain Lisp better. One of those is right here at CBT Nuggets coming from Jeff Kish. Now, good news for you, Jeff Kish is covering the SD access and the Lisp portion of this particular content in the ENSLD course. I'm going to set up a more of a less crash course for you here on Lisp protocol and how it's used within IPv6 transition technologies. But I can't encourage you enough to really dig into the Lisp protocol. You need to go to the Encore course or the SD Access course here on CBT Nuggets and check out Jeff Kish's content where he explains how the Lisp protocol actually operates in great detail, because it is a large and complicated protocol that's heavily used by service providers, but is growing in popularity from enterprises because of the deployments of SD access. The other resource that I really like for using and learning Lisp is going to be the Cisco Press OCG for the Encore and NRC exam. They also set up some great analogies of how Lisp works, and I'm going to set up one of those right now. Now, again, don't credit me for this. Credit Cisco Press for actually saying this information. Think about DNS for one moment here. How does DNS really work? When we say, hey, where is google.com, a DNS server replies with something like an IP address. I'll make something up like 160.150.140.130. That's not google.com. I'm just making it up, but that's how DNS works. We're trying to find out, hey, how do I get somewhere? And a server replies with, go to this particular server, go to this particular IP address. Lisp is not terribly unlike this. You see, the problem that we ran into, or the problem that service providers ran into, is the internet is absolutely gigantic. If you actually watched the content on BGP, you saw how gigantic it was. There were over 800,000 prefixes in a service provider's routing table. 800,000 prefixes were advertised to it. And that becomes, well, gigantic. Your CPU overhead and also using routing tables and fat packet forwarding switching and ASICs that you have, it's just massive in order to have a tremendous amount of throughput, but also a tremendous amount of routes. So they introduced the Lisp protocol to help with the scale of route tables themselves. The idea is kind of like this. Pretend host 4 wants to ping host 5, just like we've always done. It will send the packet to its default gateway, and R1, instead of having to parse through its gigantic routing table to figure out where its next hop could be, it could actually punt that decision to a server, just like a DNS server, but it's not DNS. It's using a Lisp server. The Lisp server is called a map resolver or nmap server. Oftentimes, these are separated roles. These are actually two different servers, but at the end of the day, what they do, specifically the MR, or the map resolver, is it resolves where your next hop should be. So in this case, if host 4 wants to ping host 5, R1 would ask the map resolver, how do I reach that remote subnet? And the map resolver map server would say, go to R3. So R1 would then send its packet through the domain over to R3, then R3 would know how to route it from there. Do you see how that's a lot like Google.com? It's asking, where is this destination? And a server replies where that destination is. It's almost as if it's offloaded or outsourced its route table to be a physical server, which is really kind of fascinating. Now, how does this work within an IPv6 environment? Lisp can actually become a tunneling technology that can be used for this. It works kind of like this. R1 has its 2005:/64 prefix. So I'm just going to write 2005:/64 prefix. And what R1 does is it sends that prefix to the MS, or the map server. In this case, they're both the MR and the MS. The MS is what handles advertised prefixes coming in to be resolved. Similarly, R3 participates in the 2007:/64 prefix, and it would send its prefix to the MRMS as well. So these two devices are participating in a Lisp domain, and they're advertising their prefixes towards the MR and MS. But right here on these E00 interfaces, these are IPv4 addresses. Here we have 10.0.0.1, and here we have 10.0.0.6. So when R1 sends its 2005:/64 address prefix towards the MRMS, it's going to say, you can reach me through my IPv4 address of 10.0.0.1. And when R3 advertises its 2007:/64 address to the MRMS, it's going to advertise, you can reach me through its IPv4 address of 10.0.0.6. So when it comes time for host 4 to ping host 5, the packet will be sourced from 2005, destined to 2007, that 2007 prefix, and it's going to arrive on R1. And because R1 is participating in Lisp, it's going to say, how do I get to 2000:/64? And the MRMS is going to say, you need to use Lisp encapsulation and send the packet to the IPv4 address of 10.0.0.6. So R1 and R3 form a Lisp tunnel. And the tunnel exists between 10.0.0.1 and 10.0.0.6. But the IPv6 traffic can now be tunneled in between my Lisp-speaking sites. As traffic goes out of this Lisp site, this router is going to be sending that traffic into the Lisp domain. So we call this router, R1, the ingress tunnel router. Traffic is going into the tunnel. That's another way you could think about this. Traffic that is being encapsulated into a Lisp packet is said to be coming from the ITR. And as traffic exits the tunnel, this is known as the egress tunnel router. In other words, it is de-encapsulating the traffic that is coming from the Lisp tunnel. So when host 5 replies here, guess what? That packet is going to be encapsulated into a Lisp packet, turning I3 into an ITR. The traffic goes through the tunnel and then exits the tunnel, which turns R1 into an ETR. So we see how when there's two-way traffic, it can be both an ITR and an ETR, and that is sometimes referred to as an XTR. So the major talking points that we have, and we're bringing away from this particular nugget, is that IPv6 traffic can be tunneled over IPv4 using the Lisp protocol. Our routers in the Lisp domain are usually XTRs. They allow egress traffic to exit the Lisp domain and ingress traffic to enter the Lisp domain. And they use the map resolver, map server, or MRMS, sometimes also called MSMR, to resolve where is their next destination within the Lisp domain. It basically says, take me to this particular site. So that's understanding how we can tunnel IPv6 traffic over a Lisp interface, encapsulating the traffic into an IPv4 Lisp packet. I hope this has been informative for you, and I'd like to thank you for viewing. Our last IPv6 transition method is going to be the translation method. In the same way that NAT can translate one IPv4 address, or multiple IPv4 addresses, into a different IPv4 address, we can actually translate an IPv6 address into an IPv4 address using what's called NAT64. Beyond that, we can actually translate DNS lookups from quad A lookups into single A lookups using DNS6.4. And DNS6.4 and NAT6.4 work hand in hand together in order to get IPv6 traffic destined outbound into an IPv4 network. We're going to talk about how they work together and how they actually collaborate in order to make IPv6 translation into IPv4 come to life in this particular nugget. Let's get going. Now, our last method of transitioning to an IPv6 network when there's IPv4 still all around the world is going to be the translation itself. And we talked a little bit about NAT6.4 and DNS6.4. Here's how it all really works in the real world. This is going to be kind of a big topic. It's going to be a big thing to understand, but it is important because it is kind of fascinating at the same time. So here's what we have here. In this environment, this is where our enterprise network exists, right here. This is the outbound border towards the internet where IPv4 exists. Over here, we have IPv6. And the first thing that we need to know about is that we've got two appliances that are aware that 6 to 4 translation may need to take place. The first thing is right here. We have a dedicated server called the DNS6.4 server that is dedicated to translating single A records into quad A records should there not be a quad A record. So here's my host right here. My computer down here, let's pretend is running Windows 10, which we know by default prefers to run IPv6. Let's pretend for a moment that it's only running IPv6. So when it does a DNS lookup, it's going to be requesting a quad A record. It's going to be requesting a IPv6 lookup. So what it does is it's going to send its DNS request first to the DNS server, the DNS6.4 server, who's going to be looking for a translation. The DNS6.4 server is going to proxy this request to the main DNS server, and it's going to be requesting a quad A record. If a quad A record is returned, guess what? That's great. We get the IPv6 response going back like this. And then traffic carries about the way it normally does. It uses IPv6 routing and it goes from there. But what happens though when we're trying to look up a resource and there isn't a quad A record? Maybe we're looking for a resource on the internet that only supports IPv4. So after recursive lookups take place, we only get an IPv4 record. What happens then is this DNS server is going to reply to the DNS6.4 server with a single A record, and the DNS6.4 server now has to translate that IPv4 address into a quad A address. But it uses a RFC standard address. That way, when it replies with a quad A address to the host can look at this and say, oh, I recognize that this is an IPv6 address, but it's been translated from an IPv4 record. So it knows that this is great. It's an IPv6 address, and I only support IPv6, and that's a big thing for me. But I know that as I go out to the internet, this is going to be translated into IPv4. So when it sends its packet destined to that destination to this particular router right here, it sends it in such a way that this router knows that it's going to translate this, it's going to NAT it from its IPv6 global address into the IPv4 address that would have been encapsulated in that record. So translation in this place takes place in a couple of different ways. It starts with the DNS lookup. It tries to perform an IPv6 DNS lookup, and if it can't do that, the DNS6.4 server is going to translate the A response into a quad A response that's formatted in such a way that the host knows that its traffic is about to be translated outbound towards the internet from an IPv6 address into an IPv4 address. The host then builds its packet destined towards the NAT router and says this needs to be NATed into IPv4, and that's where this router performs that NAT translation from 6 to 4, so that once it goes out to the internet, it's all using IPv4. So that's how the translation takes place in a translation-based transition technology for IPv6. I hope this has been informative for you, and I'd like to thank you for viewing. So we've covered a lot of ground in this particular skill. It's going to behoove us to take a moment to actually recap some of the content that we've covered here. We started out by talking about the dual stack migration technology. It's not really much of a technology now, is it? We're just running IPv6 and IPv4 on the exact same boxes. It's important, though, to keep in mind the design consideration about what our end-user devices are going to prefer by default, and how that traffic should be routed or distributed, or how IGP should be deployed between these. For instance, our end-user devices like our cell phones or our Windows devices are going to prefer to use IPv6 if they have IPv6 addresses before they fall back to IPv4. So I want to make sure that I have end-to-end IPv6 connectivity first. That way my devices will just use IPv6 by default. But the big talking point then becomes, what happens if we don't have IPv6 deployed end-to-end? Maybe there are limitations or WAN branches that can't make that happen because the service provider can't make that happen. Well, then we have to use our tunneling technologies or translation technologies. The tunneling technologies that we talked about were the statically or manually created ones, like the GRE, or the automatically or dynamically created ones. These are going to use 624, 6RD, the ISOTAP tunnel, or even the Lisp tunnel, which is a pretty fascinating one, and you will learn more about Lisp technologies as you progress through your ENSLD training, or even if you jump into Encore or ST-Access itself. We then talked a lot about Lisp, and we learned about the map resolver map servers, the ingress tunnel routers, and the egress tunnel routers, and how our Lisp-speaking routers will actually perform lookups for other endpoints. Those are called RLOCs, by the way, for looking up how they should forward traffic when it's destined to a specific destination. We compared it to DNS, which is actually what Cisco Press's comparison is, and how it looks up, hey, how do I get to this next hop? And the server responds with the next hop. This next hop would be an IPv4 address, and the Lisp encapsulated tunnel would be able to carry the IPv6 traffic over IPv4. Another major consideration, of course, was securing our IPv6 traffic, because a router who's sitting in line between IPv6 speaking sites is only carrying and inspecting IPv4 traffic. The router would need to be smart enough to know to look into the encapsulated payloads and actually view the IPv6 traffic to make sure that malicious traffic isn't being tunneled over IPv4 traffic, and it would have to be able to inspect that. We also talked about NAT translation, which is a pretty fantastic way of handling this, because we can translate an IPv6 packet into an IPv4 packet. And lots of times this is used in conjunction with DNS 6.4. Our routers would be able to look at packets that have been replied to with DNS 6.4 addresses, and it would say, oh, I see that this is a 624 translated address, so I know that I should send that to my NAT 6.4 router, which will handle translating my IPv6 address into an IPv4 address, and that way the traffic will be able to reach the global internet. So this is a recap of what we've summarized and learned within the IPv6 migration techniques. I hope this has been informative for you, and I'd like to thank you for viewing.